Hello, in this video, we're going to be talking about radioactivity. What does that even mean? Let's get into it. Here's what it means. It's the spontaneous emission of ionizing radiation. When a nucleus, an atomic nucleus, is unstable, it will spit some stuff out to try to calm down, and that's what radiation is. So a nuclide, you're going to see some of these words sometimes. Nuclide, fun word, is like a specific nucleus. Just like, we have different elements, different names for elements and isotopes. So defined by the nucleon number, like carbon 14 is a nuclide. And it is also a radionuclide, an unstable type of nucleus that undergoes radioactive decay. So lots of things are stable, lots of nuclides are stable, but there are plenty that are unstable and will do radioactivity stuff. We're going to get much more into these soon, but there are 3 types of radioactive decay: alpha, beta, and gamma. The preview is alpha's a kind of chunky positive charge, beta is a little tiny minus charge, an electron even, and gamma is a gamma ray. They all got some fun rules. We'll learn them. All right, here's a fun little animation of what radioactivity is, which is it's just the thing spitting stuff out, spitting off little particles. So this is uranium. This is uranium in what we call a little bubble chamber. It's in like a liquid where when it emits these particles, you see them. You can see them move through the liquid. You see these little trails that they leave. And, there it goes. It's just like constantly emitting all these little particles as there's a ton of different, any given nucleus of an atom inside of that chunk of uranium might at any point decide to spit something out. And there they are, the little particles flying off. That's all radiation really is particles flying out of a thing. Okay, there's some amazing rules about how that happens, though. And very spooky, very unlike what we're used to on our large scale. But when we get down to this level, lots of things are probability based, probabilistic. So decay is a spontaneous and probabilistic event. It is impossible to predict when a nucleus will decay. You could know everything you might possibly want to know. You could measure anything you might possibly want to measure, even without any uncertainty at all, if that's even possible. But you would never, ever, ever be able to predict it, which is crazy. Most stuff in physics, like, that's not usually how the universe works, we thought. If you know enough, measure enough about a ball flying through the air, you can certainly predict exactly where it's going to land because the laws of physics give you like an answer like that. Well, the laws of physics here are probability based. It's bananas. Here's a number that describes this a little bit called the decay constant. We use lambda for the decay constant. That is the probability of decay per unit time measured in any kind of time unit to the -1. So like per seconds or per minutes or per years, depending on the thing and whether it hangs around for just a couple seconds or many, many years or whatever. And it's like implied that there's a percent per second or a percent per year. So let's look at some numbers to see what that means. Okay, so like for example, carbon 14, the decay constant is this teeny tiny number, 3.84 times 10 to the minus 12 per second. Radon 220 is, 0.0133 per second. And the idea is this is a probability, so this is a percentage, the 0.01 whatever, means 1%. So this means there's a 1.33% chance per second. So 1.33% chance that in the next second, if you got yourself a little radon 220, a single nucleus of it somehow, there's a 1.33% chance that any given nucleus of radon 220 will decay in the next second. And remember how statistics work. Then if it doesn't decay in the next second, how likely is it to decay in the following second? Still 1.33%. Yeah, so that's the idea. It does, the Abbey wants you to kind of be aware that this is only for small time intervals, so this is almost like an instantaneous probability. Um, this gets weird because of the way Half-Life works. This doesn't mean that if like 100 seconds go by, it's definitely going to decay. Like that's not how probability works, right? It's never 100. You could flip, 100 quarters, 50% chance each one lands on heads, but it is possible that they all land on tails. Um, Pretty unlikely there, but that's the idea. Statistics is weird. So it's a percentage chance, like an instantaneous probability is a good way to think of it. All right. And another number that we use that you likely have heard of to talk about the kind of probability of something decaying and how long it takes to decay is called half-life. Because here's the idea, even though you can't possibly predict when a single nucleus is going to decay, statistics say that when you have lots and lots and lots and lots of something where there's probabilities involved, things become very predictable. Um, right? Take flipping a coin again. If you flip a single coin, you can't really predict which side is going to land on. It's like a 50-50 shot. But if you flip 10 coins, you can be more confident that like about 5 will land on heads and about 5 will land on tails. But definitely there's room for lots of differences there. But it's probably going to be close to half and half. If you flip 1,000 coins, it's definitely very likely that you can predict that it's going to be very close to 50% land on heads, 50% land on tails. If you flip 5 trillion quarters, it is going to be extremely, extremely, extremely close to exactly 50% heads, 50% tails, right? Law of large numbers, big sample sizes, you can do statistical average stuff. That's what Half-Life is. When you have a whole bunch of nuclei, which is the usual case, right? Like a chunk of uranium has a unfathomable number of atoms in it, so a huge, huge, huge number of nuclei. Once you have a lot, we have a very good idea based on the decay constant of how long it will take on average for half of those to decay. And the math of this is pretty fun because this is how exponential stuff works. It halves over a certain time interval, and that's always the same. Whether you have 5 billion uraniums or 500 uraniums, the time it takes for, well, maybe 500 is not a great sample size, but, no matter how many you have, as long as you got a bunch, the time it takes to decrease by 50% is always constant. So let's look at that. You're going to see curves like this, decay curves, which show how the amount of radioactive stuff decreases over time because when it decays, it turns into something else. So this is like percentage up here. And yeah, here's the idea. When a half-life goes by, the amount of stuff cuts in half. So if it's uranium, a uranium nucleus will spit out a thing, and often what it's spitting out is something like a little lump that's got protons in it. So uranium nucleus is like kind of big and unstable, and it spits out some protons and neutrons. Well, by spitting out protons, that means the element is changing. And so it changes from uranium into something else, and you have less uranium. Then you have other stuff. We call those the parent and the daughter. The thing you start with is the parent. The thing it decays into is the daughter. So as this curve goes down, you have less and less and less of the parent and more and more and more of the daughter is going to be the idea. But okay, so in this case, it looks like the half-life of this thing is 25 seconds. So you start with however much, let's call it 100%. 25 seconds later, you're going to expect to have 50% left. And then 25 seconds later, you're going to have half of that, 25%. And then 25 seconds later, you're going to have half of that, 12.5%. And so on, so on, so on. And it turns out, like, this is how exponential math works. If something keeps halving and halving and halving, for example, that's exponential decay. And HL students, especially, we will get into some of the fun math of like exponential decay curves and doing, e to the whatever and natural logs of stuff, because you can write some equations for graphs like this. So we'll get there. Okay, before getting to the exponential decay curve math, there are some like more straightforward problems even that the IB will give you, which is when you have like an integer number of half-lives where they just say something like, 4 half-lives have gone by, figure something out. Really, all you got to know is a half-life means it's the time it takes for the thing to cut in half. If you would like a sort of step-by-step thing, here's a good way to think of it. Is to find the percentage remaining, you do 1 over 2 to the number of half-lives. This just means you divide by 2 n times. Yeah, but this can be convenient, especially if you have a lot of half-lives. If it's like 12 half-lives go by, you really would just divide by 2 12 times, but that would be annoying and easy to lose track of. So this is a nice way to do it. 1 over 2 to the 12 is dividing by 2 12 times. And then watch out. Often, the IB likes to be tricky. They will sometimes ask you like about what's remaining for the parent, but they'll sometimes ask you like how much of the daughter do you have? And it's like if 75%, um, if the parent has decayed to like 25%, say like 2 half-lives have gone by, you got 25% of your stuff remaining is the parent. They might ask you about the daughter here, and you got to be like, oh, well, now 75% of the stuff is the daughter because only 25% is the parent. Like they're always going to add up to 100% or the same total mass, that kind of thing. Okay, also, HL people, you have an equation for the half-life of a thing, just to show you it now. And here it is. T with a little 1/2 like that is how we're going to write half-life, and it's based on the decay constant. And because we'll get here, we can even look at where this comes from soon. But there's some fun like e to the something equation math where we get a natural log. So what happens is you get the half-life as the natural log of 2 divided by the decay constant. All right, so be careful, especially my gamer nerds. This thing does not mean half-life. We just use T 1/2 for the half-life, which is the amount of time it takes for a sample to cut in half. And it depends on the thing. Some of them decay super quick, so I'll probably use seconds. Some of them take billions of years, and we'll say years or whatever. The decay constant then is like per second, per minute, per year, so they'll match. All right, let's try one. Let's see if we can solve one with integer number of half-lives. There's your hint. Let's say you got yourself some zinc 71, which is radioactive. You have 300 grams of it. After 7.2 minutes go by, how much of that sample, mass-wise, is still zinc 71? How much zinc 71 remains? Go ahead, pause the video, try that, see what you come up with. Okay, let's see how you did. The half-life is 2.4 minutes, so the first thing we got to figure out is how many half-lives have gone by. 3, it's 3. There's 3 2.4s in 7.2. We should divide those to try to figure that out. And so the amount of zinc 71 is going to cut in half 3 times. So you divide by 2 3 times. In other words, you divide by 8. In other words, you take 12.5% of your starting amount. Right, so I'll do it this way. 12.5% of 300 is 37.5. That's the same thing as 300 divided by 2, divided by 2, divided by 2, which is the same thing as 300 divided by 8. All right, all those ways of thinking of it, you get 37.5 grams of that sample is now zinc 71. The rest of it is something else. All right, and radioactivity is a thing you can actually like put a number on. We usually call it activity, capital A for activity, and it's the rate of decay. It's how often it's decaying. So how many times per second is what it's going to be. How many times per second does this sample, a particular sample, do decay? So the unit for this is the becquerel. It's like after a French gentleman, capital B, lowercase q, just like as one thing. That's the unit, and it means 1 decay per second. All right, so like if you have a block of uranium in front of you, and every second you see 500 little particles shoot out of the uranium, It's got a activity of 500 becquerel, 500 decays per second. Okay, so here's the thing. We've tested a bunch of stuff. The only thing that affects uh, how how radioactive something is how much of it there is, because each little nucleus just has a certain percentage chance, and that's all it is a percentage chance. So depending on how many nuclei you have, um, there's a certain rate, number of things per second, number of decays per second that are going to happen statistically speaking, and you can't change that. We tried everything. If you change the temperature dramatically around something, it won't change the rate of decay. If you change the pressure, super high pressure, put it in a vacuum, if you apply strong magnetic or electric fields, none of those things change the activity. The only way to make something less radioactive is to have less of it, which means the only way to have less of a radioactive substance is to wait. All right, so again, here's like a little decay curve you might see, this time with activity. It turns out the number of nuclei decays exponentially, and so does the activity, because the activity depends on how many things there are. So this also does exponential decay. You might start, you got a thing in front of you, and 80 times per minute, you're seeing a little particle fly off of that thing, a little more than once a second, right? And then it looks like here, our half-life is 2 days, because 2 days later, that thing you measured again, you put a little meter in front of it, and you're like, ooh, now this is doing 40 decays per second. And then 2 days later, it's going to be doing 20. Yeah, so the activity decays exponentially with the same math as the amount of stuff. All right, and finally, especially when we're measuring stuff, something we have to think about is background radiation. Guess what? You are being irradiated right now, constantly. There's radioactive decay all around you. Duck, wait, a particle's flying at you. No, it's okay. This is normal. This is life on Earth. We've adapted to it because there's radioactive stuff around. There's lots of radiation on Earth, and it's okay. Lots of it's very normal. Okay, try to avoid this one though. Radon gas. Radon gas is all over the place. You may have a little sensor in your basement, if you got like a basement, for radon gas, because it is like odorless, colorless, radioactive gas that's floating around. There are radioactive elements in like rocks and soil and even like building materials. So your walls might be radioactive, especially the walls of a building that's got like stone walls. There's cosmic radiation, which is radiation reaching us from space. If you, whenever you like go on a plane ride, you're getting a good bit more of this because you're a lot higher in the atmosphere. So a lot more of that radiation is there than makes it to the ground. So you get, a little more irradiated than usual when you're taking a plane ride. Also fine. If you're flying every single day, you maybe got to think about that. There's lots of medical procedures that use radiation, like, CAT scans, this kind of thing, like radiotherapy. You're using radiation in those cases to, like, measure stuff, treat stuff. X-rays are one of these. Yeah, and so there's a certain amount of radiation, like dose, that you get with each of these procedures, and some will give you much more radiation than others. So that's something that you, are kind of keeping track of. The doctors are, to make sure you don't get more radiation like in a year than you are supposed to. Yeah, but so if you're freaked out when the dentist comes in the room and is like, "Okay, I'm going to give you an X-ray," and they put a big lead bib on you, and then they set up the little X-ray doohickey, and then they're like, "Okay, this is totally safe and fine. Don't you worry at all. But I'm going to go step out of the room and hide over here and press this button." Yeah, it's fine. That's because they do it every single day. If you were exposed to a dental X-ray every single day, that would be too much radiation. But once every 6 months or a year or whatever, that's fine. That's fine. Okay, and everything gives off radiation, all living stuff. With like, there's a carbon and a potassium mostly that are radioactive, that are in living stuff. And especially bananas. Bananas have a ton of potassium and they are pretty radioactive. Yeah, so, if you got a banana in the house, be careful. It's irradiating you. But again, it's fine. All of this stuff, there's like a background count that's not at all really dangerous to human life, but it is something happening all around us all the time. So if we're trying to measure radioactivity, we have to account for the background. Also, we're saying nuclear power. You might think that this would be like where a lot of radioactivity around you is coming from, that we have like nuclear power plants and stuff. It is not at all. You get like your normal daily radiation dose is less than a tenth of a percent comes from like nuclear power. So there's way, way, way more radiation around us than anything we're kind of making with nuclear power. There's something like even if you live next to a nuclear power plant, you'll get more irradiated in a day if you eat a banana than if you do just by kind of living there. All right, so that's kind of where this comes from. And so what you do if you are taking a measurement is you have to subtract that background away. So you would have to measure the background amount and then take that away. Yeah, so you would measure like a curve that looks like this that doesn't decay down to zero. It would be decaying down to like the background level. And to use most of our equations and to use like the half-life idea, this has to be, you know, approaching zero at the end rather than approaching the background count. So you got to measure the background count and subtract it away. If you got a little block of uranium in front of you, you take it away for a minute. You go stick it in a closet somewhere. Then you get yourself a little meter and you measure the amount of radiation without the thing there. And then you put the thing there and measure the radiation so you can figure out how much radiation is coming just from it. So this is mostly a like when you're doing experiments and measurements and stuff, but sometimes it comes up on the exams. If they talk about the background count, that's what you want to do. You would measure the background and then subtract it away, and then you could do math on your like corrected curve. All right, and there you go. That's radiation, your little intro to radiation. We'll be getting more into like the different types of decay and how the elements change into other elements and some of the math of these curves for HL people. So lots of fun to come. All right, see ya.